This presentation is based on our paper on a localized Lagrange multiplier approach for the problem of vehicle-bridge interaction published in the Engineering Structures Journal. The presentation starts with a brief introduction on the numerical treatment of vehicle-bridge interaction. Then it demonstrates the main premise on which the proposed algorithm is based and the formulation of the problem via localized Lagrange multipliers. Following numerical applications illustrate the advantages of the proposed algorithm compared with existing numerical analysis schemes to solve the vehicle-bridge interaction problem. Finally, the main features of the proposed approach are summarized. The focus of the study is on the numerical treatment of vehicle-bridge interaction. Thus, the introduction part focuses solely on current techniques to numerically treat vehicle-bridge interaction. Time integration algorithms to solve vehicle-bridge interaction, or in short VBI, are mainly divided into two categories: iterative algorithms and coupled algorithms. Iterative algorithms solve the vehicle and bridge subsystems separately, considering the contact forces as external loads on the two subsystems. The separate treatment of the vehicle and bridge subsystems decreases the computational cost of the analysis. However, the solution of the system relies on iterations at each time step until a compatibility condition is met. As a result, the convergence of the solution relies on the number of iterations at each time step and also on the update procedure at each iteration. Coupled algorithms, on the other hand, solve the vehicle and bridge systems as a gathered system, which ensures the accuracy of the obtained solution. However, the gathered system matrices are time-dependent as they change with the location of the vehicle and the bridge. Thus, the involved computational effort may be increased. Motivated by the limitation of existing coupled and iterative algorithms to solve VBI, we developed an novel algorithm to solve the VBI problem both accurately and efficiently. The proposed numerical algorithm aims to solve the VBI problem in a robust, accurate, and cost-effective manner. To this end, the proposed approach partitions the coupled vehicle-bridge system. The partitioning relies on the introduction of auxiliary contact bodies between the vehicle and the bridge. This allows the separate treatment of the vehicle and bridge subsystems, which can be proven valuable in certain applications and can possibly reduce the computational effort of the numerical analysis. The auxiliary contact points also ensure the compatibility of the involved constraints. More specifically, via the auxiliary contact points, two sets of Lagrange multipliers are applied to the vehicle and bridge subsystems. One between the vehicle and the auxiliary contact bodies, and another Lagrange multiplier between the auxiliary contact points and the bridge. Importantly, the vehicle and the bridge equation of motion are independent of each other. In addition, via the introduction of auxiliary contact bodies, two sets of kinematic constraints between adjacent systems can be formulated. The compatibility of the constraints is ensured via the Newton's third law. The Newton's third law dictates that the Lagrange multipliers pertaining to the vehicle and bridge systems should be the same. Eventually, the system can be described via 5 equations: the equations of motion of the vehicle and the bridge, the kinematic constraints between adjacent subsystems, and the Newton's third law. The solution of the system requires partitioning of the equation of motion. This means that we first estimate the Lagrange multipliers and acceleration of the auxiliary contact bodies, which then substitute into the equation of motion of the vehicle and the bridge. The vehicle and bridge subsystems are not coupled, thus the system matrices do not change in time, which increases the computational efficiency of the analysis. In addition, the vehicle and bridge systems can be solved in parallel, which can further decrease the computational cost of the analysis for large vehicle-bridge systems. At the same time, the compatibility of the constraints is preserved at each time step. Thus, for the linear VBI problem, there is no need for iterations. To demonstrate the accuracy of the proposed localized Lagrange multipliers algorithm, two configurations are examined. The first configuration considers a benchmark vehicle-bridge system consisting of a simple sprung-mass traversing a simply supported bridge. The proposed localized Lagrange multipliers approach is in excellent agreement with different numerical algorithms from the literature, including both coupled and iterative algorithms. Also, as expected, the localized Lagrange multipliers pertaining to the vehicle and bridge systems are the same. The second system, to demonstrate the computational efficiency of the proposed localized Lagrange multiplier method, examines a Nate vehicle train traversing an arc bridge. The proposed algorithm appears to be in perfect agreement with the coupled algorithm to solve the VBI problem. On the other hand, the iterative algorithm shows some discrepancies when the number of iterations is insufficient. Importantly, the proposed algorithm is also computationally more efficient compared with existing algorithms to solve VBI. Specifically, compared to two coupled approaches, the proposed localized Lagrange multipliers method appears to be 10 times faster. Compared to an iterative algorithm, the proposed partitioned method is 3 to 4 times faster, depending on the time step of the time integration. Lastly, I will close this presentation with the main feature of the proposed localized Lagrange multipliers approach. The proposed approach introduces auxiliary contact bodies between the vehicle and bridge subsystems. This way, it assigns them the vehicle and bridge with localized Lagrange multipliers that allow the separate treatment of the two subsystems. The auxiliary contact points also preserve the compatibility of the constraints at each time step, thus no iterations are needed. Lastly, the partitioning decreases significantly the involved computational effort, especially in the case of demanding vehicle bridge systems.